Hello, in this video we'll be talking about section 2.2, systems of equations with three variables. We had already discussed what a system of equation of three variables are, but here we are going to explore a couple more problems concerning those. First, if we look at problem 1 here, it says, is 2, -1, 3, keep in mind this ordered triple would represent coordinates for x, y, and z, respectively. We want to see if this is a solution for the system that we have on the right side here. We're going to show how we know that. In order to confirm if that is a true solution, what we're going to do is take each of these three equations and make sure that this point is a solution for all three of them. We don't just want to check one or two of them, because we could have scenarios where one or two of these equations overlap, but not all three. We want to check if this is a true solution for the full system, so we want to check all three equations. Therefore, let's take that first equation, x plus y plus z equals 4. So I'll call this one equation 1. So for equation 1, I'm going to plug in those coordinates x, y, and z into that equation. X is 2, y is -1, so that's plus -1, and z is 3, so that's plus 3. And we want to show that that is equal to 4. If we plug that in, 2 plus -1 will give us a total of 1. 1 plus 3 then is indeed 4, which means we do have that this is a solution for at least the first equation. Let's check the next one. So I'll call the second one equation 2. It's always good to label these equations. For equation 2, again, I'm going to be plugging in the x, y, and z coordinate that we have here in. So 2 times the x coordinate of 2 minus 2y, where the y coordinate is -1, and then minus z, where the z coordinate is 3. We want to show that overall equals 3. If we calculate this out, 2 times 2 is 4, minus 2 times -1 would be overall plus 2, and then minus 3 equals 3. On the left side there, we have 4 plus 2, which is 6, and 6 minus 3 is indeed 3. So that means that this also checks and works for that second equation. But again, just because it works for two of them doesn't mean it works for all three. So let's check the third one as well. Call this one equation 3, and let us check that one. Yet again, I'm going to be plugging in my x, y, and z coordinates in for x, y, and z for this equation. So if x is 2, I'll get -4 times 2, plus y, which is -1, plus 2 times z, and z is 3. We want to show that this will equal -3. We do that, -4 times 2 is -6, plus a -1 is also -1, and then plus 2 times 3 is plus 6. We combine those together, you'll notice that we have a plus 6 and a -6, which those will cancel out, and what we then get is -1 equals -3. This is not a true statement. -1 does not equal -3. Therefore, the coordinate that we have of 2, -1, 3 may be a solution for two of the equations, but not all three, and therefore it is not a solution for the entire system. So my answer for this is no. It is not a solution because it does not work for the third equation there. All right, let's look at one more example of this, and we'll do so by looking at the general flow that you will have when trying to organize these kinds of problems and solving for a full solution. First, state the problem if it's not already, or for example, if the system of equations are not collected together. This also should be when you reorganize things, so if the equations are not in the same format of ax plus by plus cz equals the constant term of d, then rearrange that. Or, for example, if your equations have some fractions or decimals, see if you can clear that out. That would be part of this step. Then we're going to eliminate variable 1, which could be x, y, or z. It is up to you. from two of those equations, and we'll eliminate that same variable from another set of two equations. Then we'll use those two equations that we found, which we'll call typically equations 4 and 5, to find variables 2 and 3. So, for example, if we elected to eliminate y, then that means we would be using our two new equations to solve for x and z. Once we then have those, we will plug those in to one of the original equations. It's up to you which one, 1, 2, or 3, and solve for whatever variable is missing. That's the general flow. Let's demonstrate how we would do that with the example here. Here we have the system of equations 3x minus y plus z equals 4, and x minus 2y plus z equals 0, and lastly x minus y minus 2z equals negative 7. We're going to see if we can find a solution for this, either a single solution, infinite solution, or maybe no solutions. Here, based on the guidance, we're going to try to use two of these equations to eliminate the variable y. First, though, I'm going to label each of these. So let's call the first equation 1, I'll call the second equation 2, and the third equation 3, just to keep it simple. Now, if we're going to try to eliminate y, we can really choose whatever equations I want, but looking at these, I notice one of them has a minus y, one of them has a minus y as well, which means those are probably going to be a little bit easier to cancel out, at least compared to the other one that has a minus 2y. So what I'm going to actually do is I will take equations 1 and 3 first and try to eliminate y using those two. So let's try that. I'm going to take 3x minus y plus z equals 4, and I'm going to try to do something with that third equation to eliminate y. Now, if I were to just take that third equation, x minus y minus 2z equals negative 7, and I were to add them together, then this is not going to eliminate y. I would get a total of negative 2y from that. So that's not going to work. Instead, what I'm going to do is subtract the second equation. That will work out pretty nicely because minus y minus a negative y would be overall plus y and cancel out that y term. If I do that, though, everything will thus need to be subtracted in that order. So 3x minus x will give us a total of 2x. Negative y minus a negative y will give us a total of 0. Z minus a negative 2z will then give me plus 3z. And 4 minus a negative 7 for the constant term on the right side would be 4 plus 7, or 11. All right. So let's then try to do that again for two of the other equations and eliminate y, so we get two new equations, which I'll call this new one that I have down here, I'll call this equation 4. And let's try to find a fifth equation that I can combine that one with. To do so, I'm going to combine a different set of two of the original equations. I already did 1 and 3, so I can either do 1 and 2 or 2 and 3. Again, it is up to you. I like equation 2 there because it does have a 0 for the constant, and I'm going to choose equation 1. Not for any particular reason, it's really up to you. I only chose that really because the constant term for the first equation is positive. That's maybe my only inkling there. If I take that first equation of 3x minus y plus z equal to 4, unfortunately that will not combine very nicely with that second equation to eliminate y. I can't add them together or subtract them like I did in the first case to eliminate the y term. But if I multiply one of those equations by a constant term, I can get a new version of that equation that can combine with the other one. So what I'm going to do here, there's a few ways to approach this, but I will choose to take that first equation and I will multiply it by negative 2. The reason for that is because negative 2 times negative y, I'll put this on the side, negative 2 multiplied by negative y is going to give me a positive 2y. And positive 2y will combine very nicely with that second equation to eliminate minus 2y. That is why I choose to multiply by that constant. If I do that, negative 2 times 3x will give me negative 6x. Negative 2 times negative y, as we said, will give us plus 2y. Negative 2 times positive z will give me minus 2z. And lastly, negative 2 times 4 will give me negative 8. Then I'm going to be taking that equation along with the second equation from my original set, adding them together and creating a new fifth one. So I'll be taking this new equation of negative 6x plus 2y minus 2z equals negative 8, and I will add that with the other equation, x minus 2y plus z equals 0. If I do that, negative 6x plus x will give me a total of negative 5x, negative 6 plus 1. The y terms, 2y and minus 2y, will add together and create 0, which is intended. The z terms, negative 2z plus 1z, will give us a total of minus z. And our constant terms, negative 8 plus 0, will just give me negative 8. So that means I now have a new equation, which I will label as equation number 5. And I can now use those in my next step to try to get one of these variables solved. So as I said, I'm going to be taking those two equations, 4 and 5, using them to solve for the other two variables that they both include, which is x and z. And I can do so in whichever order. Looking at my two equations, I have 2x plus 3z. The other equation, I have negative 5x minus z equals negative 8. Just looking at that, I think z is probably the easiest one to eliminate there, as I would only need to take one of those equations and multiply it by a constant in order to eliminate the other one. If I try to take 2x and 5x, unfortunately those do not have a number where I can say multiply 2 by a number that's a whole value and create 5. Instead, I can take that second equation, multiply it by 3, and eliminate the positive 3z from the fourth equation. So I'm going to again take equation 5. Negative 5x minus z equals negative 8. And I'm going to multiply that by 3. This way, when I combine it with the fourth equation, the z terms will cancel. If I do that, 3 times negative 5x will give me negative 15x. 3 times negative z will give me minus 3z. And 3 times negative 8 will give me negative 24. Using that new equation, negative 15x minus 3z equals negative 24. I can combine that with equation number 4. 2x plus 3z equals 11. I can add those two equations together and cancel out z very nicely. This will give me negative 15x plus 2x will be a total of negative 13x. The negative 3z and the plus 3z will cancel out to create 0. And then on the other side, I get negative 24 plus 11 is negative 13. Then I have negative 13x equals negative 13. Negative 13x equals negative 13, which I can solve for x then by dividing by negative 13 on both sides and getting a very nice simple answer for x to be 1. Now that I solve for one of those variables, I now have the value of x. I will stay here and plug x equals 1 into either equations 4 or 5, whichever one I so choose. I'm going to use equation 4 because there's more positive numbers there. I like positive numbers. So I'm going to take equation 4, that 2x plus 3z equals 11. I'll plug in 1 for x and attempt to solve for z. This will give me 2 plus 3z equals 11. I will subtract 2 on both sides to get 3z equals 11 minus 2 will be 9. And then I can divide both sides by 3 to get a final answer for z, as 9 divided by 3 is 3. I have now solved for 2 of the values in this triple I'm trying to create, and now I'm going to plug both x equal to 1 and z equal to 3 into one of the original equations, it's up to you, and solve for the final variable of y. I'm going to personally select equation number 2 at the top, and the reason for this, really it's arbitrary, but I see both a single x and a single z, so it's going to be easy to plug those in, and I see a constant term of 0. I like working with 0. So I'll take that second equation, x minus 2y plus z equal to 0. I will plug both 1 and 3 into x and y respectively. So 1 minus 2y plus 3 equal to 0. I will combine the like terms. The constant terms of 1 and 3 will make a total of 4 minus 2y equals 0. I can subtract 4 on the other side to get negative 2y equal to negative 4. And lastly, I can divide everything by negative 2 in order to get a final answer of y to equal negative 4 divided by negative 2 is positive 2. With this, I now have my solutions for x, y, and z, but to write my final answer, I will do so as an ordered triple. We write the ordered triple as x, y, z, so that would be 1 for x, 2 for y, and 3 for z. This would be my final answer for this problem. I hope that helped give you some more experience for solving linear equations involving 3 variables. Have a nice day.